Thanks, Carol, to introduce me, and it's an honor to be here presenting the project 125 Greenwich. As she spoke about, our firm, our office was founded in 1983 by Mr. Vignoli, and then most of the project we do is, marked by the sustained structural originality that presents passing phase of architectural movement, which means that we're not bound by any certain style or movement of the design. We're more about, what is the best, form or structure or system which makes the great architecture for the site or for the place the building is going to be. So, and then we have the same approach we're using for all these skyscraper, super slim, tall towers in New York City and other cities we're doing. So we have offices in North America, South America, in Europe, and then we have projects in North America. Since Rafael is from South America, we have a lot of projects in South America also, and then we have office in London, which we are doing a lot of projects in the UK, and then we also have a lot of projects in the Warwick, and also built in Asia and the Middle East. And then these are the tall buildings we have done so far in our office. Some of them are built, some of them are in construction, some of them are in design, starting from 432 Park, which was in an exhibition for this, Sky High in the Skyscraper Museum, and then we're going to talk about 125 Greenwich today. And then we have some other projects, and then we also have Walkie Talkie Building in London. So 125 Greenwich is actually very close from here. You can probably see the building going up as you're going out after the presentation. And then, so it's in the downtown area. Kind of broken.
Yeah.
Screens are a little broken, but it's in the financial district. And then it is right south of the memorial. It's very close to the 9/11 site. And then this was, that was the existing building before we got on the project. And then when we first got the project, the brief was that create a unique residential tower, which basically meets the neighborhood, which is rising as a new residential neighborhood in downtown. Because in the downtown in New York City, not that long ago, it was not considered as a really good residential area. But now it's becoming more like a really, really, uprising residential market in Manhattan. So there are many unique aspects about this building design, but tonight I'm going to focus on some of the zoning challenges we had, and then the way we overcome that zoning challenge, which was the setback issues of this building. So the tower, the site was bound by 9/11 World Trade Center Memorial Site, where you can see the 4 World Trade Center right here. And then now there's a Marriott Hotel right here. And then we have a W Hotel to the south. And then to the south of this, we have American Stock Exchange Building, which is a landmark building right next to our site. And then from there, most of the buildings are basically street wall type of the old, pre-war buildings, which is, a lot of them are actually a landmark. And then, so hinging from our site, you have brand new towers of 1 World Trade Center, 4 World Trade Center, and then you have Oculus. And then, so all this new tower with a memorial to the north, and then we have very, very traditional New York City downtown street wall architecture to the south. And because we had air right, which was bought from the American Stock Exchange Building, which is landmark, so they were not able to build any more height to their building. So the owner bought the air right of the building. So because of those air rights, we had a tremendous amount of square footage we could build onto this tiny little site, which is barely 80 feet wide, 100 feet long. So, but even though the site was small, our zoning lot itself was much bigger because our zoning lot includes Stock Exchange Building, which is, spanning block from block to block. So because of the total zoning lot sizes, we had a bigger setback than normally this tiny site will have. So by the zoning, we had to comply with the 20-foot setback on both Greenwich Street on this side and the Thames Street on the north side. So those are the pictures of the site before the project. So to make the so we first tried to make the zoning work. When we looked at the site, if we do the 20-foot setback, so our argument was basically, because we, in the end, we concluded that the 20-foot setback for the zoning for this project was not feasible because that makes the building much smaller and slender and even taller than what it is now. So if you look at the slides, so this was the 20-foot setback scheme we did. And then to study the scheme, we came up with the minimum dimension of the room sizes, and and the minimum width of the room, minimum depth of the room, and things like that. And then we found that to make the 20-foot setback work, we ended up having very inefficient spaces in the end, which makes the building very, very unfeasible. And then efficiency goes down. Because if the building is smaller, it's going to be taller. So we need more elevator, which takes up more space from the circulation point of view. So we had a very low efficiency with the 20-foot setback because of the height of the building. So what we proposed was that instead of 20-foot and 20-foot setback, we proposed smaller setback, so we can build a bigger plate, and then we can build a shorter tower. So we proposed 10-foot setback on the Greenwich Street side, and then we also proposed 13-foot setback on the Thames Street side. We proposed a slightly bigger setback on the Thames Street side because Thames Street, if you have a chance to walk the Thames Street, it is really, really narrow street, and then we have a hotel going up, which is already built and used right across the street from the Thames Street. So our building is extremely close to the building. So we wanted a little bit more buffer on the Thames Street. So we made that Thames Street. And also the depth of the building, if it is too deep, the efficiency is not really working that well. So when we studied the optimal depth of the unit and then the distance from the neighbors, we decided 13 is an optimum dimension for the setback on the north side. So we create this little image to convince the BSA board and the committee board that we needed a variance of the setback dimension, saying that if we do as of right building, which we can do, the building is going to be over 1,000 feet tall, very slim, and then it's going to be very challenging, and also it's going to be kind of out of context from other tall towers on the site. So. But if we do the smallest setback by variances, we can do a slightly shorter tower, much more efficient, and then it's going to fit into the surrounding buildings around them. So kind of hard to see here, but the height around our project is fairly tall, but if we fit within the 900 feet tall building, that realm, basically our building is going to look like the last piece of the World Trade Center site, because all these tall buildings around the World Trade Center site, starting from World Trade Center, all starting from the World Trade Center is kind of coming down in terms of the height. And then we propose that instead of having very tall building sticking out, we said, if we can get the variances, we can do the tower within the height around the building, which fits more better than the as of right. And also, Steve did some engineering comparison between, So just so you know, in terms of ratio, this project, the BSA, which is a current scheme, had a slimness ratio about 1 to 14. And then if we go with the, as of right, with the 20 feet setback, this could have been like 1 to 20, even more. So there's no comparison in terms of engineering. So it's kind of hard to see here, but this was the original scheme we proposed for the competition, and then that was the BSA scheme when we went to the BSA board. And then, so that was the major part of the design for the BSA and then setback variation to get the height, to get to the point where we have the height of the building as of now. And then that was a typical plan at that time. So at that time, the building was actually planned for the rental building. And then there was a market change in 2015, and then the client wanted to change the project from the rental to the condo. And then when that happened, we looked at the both option again, because for super slender tall building, client wanted to look at an option of actually doing the condo with super slim, which is as a right scheme. And then in the end, we basically convinced the owner that the BSA scheme is more efficient and more feasible, even for the even for the ultra luxury. And then one of the factors which basically made a decision possible was that the market of the downtown in this neighborhood is completely different from Midtown. So if you think about the 432 or the 57th Street, all these 57th Street projects are, all the units are very large, So 432 has 1,300 square feet, one bedroom apartment, which is very rare in New York City. In this neighborhood, in downtown, basically we're saying no one's going to buy 1,300 square feet, one bedroom unit. So this is more of the market for young professional with probably 1 kid or no kids, starting a career, working in a financial district, and so the unit's going to be much more smaller sizes, and then it's going to be more towards the 1-bedroom studio and 2-bedroom units, and a very small number of the 3-bedroom units. But it's going to be very luxury too, because of the height and then because of the neighborhood also. So for that reason, we basically decided to stick with the BSA height, BSA setback dimension, and then turn it into the condo building. So that was Rafael's sketch for the new design. That is the final design as it's going up. And then, a few things about the new design, not the new design, but the final design of this tower is that we have rounded corner, which happens to be very common in this neighborhood. I don't know why, but which helps a lot in the wind. And then we also have a break in the middle, which actually serves as a mechanical space, which feeds the waters and heating and all these things up and down the building, which helps the efficiency of the building. So we don't have to keep all the any of the mechanicals within the residential floor. So, and also that acts as a windbreak for the building, which is similar to the 432. We created this one mass in the middle of the building, which creates the pathway for the wind to go around the building. Next slide, please. So that was the physical model for the project. And then next slide. That's the elevation. So the slenderness comes in with the west elevation, not with the north elevation, because you count the smaller dimension for the slenderness ratio. And then that is basically 1 to 14, which is basically same as a 432. 432 is much taller, but it's bigger footprint. So the slenderness ratio-wise, this is actually the same as the 432. And then the other thing about the new tower, the final design was that when we decided to go with the condo with the new design, one of the move the owner made was that putting the amenities for the tower to the top of the building. So you can slightly see the top floor over there is a double height. That is actually a pool for the building. So the argument was basically that Raphael actually made this argument that if you are selling this apartment for the young people who's basically spend their night at 400 square feet studio, what they need is they need a very, not everybody in the building is going to have a great view. So the one way of basically appealing to the market is that you can have the view, whether you're living on a 3rd floor or 50th floor, you can go up to the top of the building for your lounge or for workout, for swimming, and then you can enjoy the view. Everybody in the building can go up to the top and enjoy the view. So, but it's not, it's not easy because naturally you want to put the most expensive apartments at the top of the building, but having the amenity on top has very unique aspect, and then which is very, very appealing to the market. In the next slide. And also Steve's going to talk about a lot about the structure of the building, and we also have very strong structure, which basically holding the building, but also that works with the layout of the building. So we use the structure, which is big shear wall, running north and south, and across the building, to basically we use that structure to basically compartmentalize the plant. So we can use that for demising between the units and combining units and things like that. So we can see that in the plan. And then we also created the very unique podium in the tower. Actually, the podium of the building, since we moved all the amenities, which is normally in the podium, to the top of the building, we have podium, which is residential units. So what we did there is that we don't have plan for the presentation tonight, but we also have loft unit here, which basically kind of like follows the American Stock Exchange building scheme, design language. We have very tall windows, and then within that window we have loft unit looking down the memorial. So this is looking north. So we have a forward trade center right north to us. So north view is kind of limited if you're dead on to the north, but we are very open to the west and the east. Next slide. And then the west view is just amazing. And then if you look at the plan, because of these kind of view limitation, or more open to the west and east, little limitation on the north, we basically place the shear wall, north-south way, and then east-west way inside the building, but the north-south to the perimeter of the building, and then that is actually working very well for the structure also. So as I mentioned, that the uniqueness about the structure is that we have basically two I-beam shape, which is holding the building, and then that basically creates one side of the building, the middle part of the building is part of the building. So that basically determines the layout. So we have 2 units sometimes, we have 4 units sometimes here, and then the middle becomes a studio or sometimes a master bedroom. And then east always becomes a one bedroom corner unit. Sometimes it becomes a penthouse unit with a 2-bedroom layout. So next slide. You can see that this becomes now 2 units. Before it was a 4 unit. In the next slide. This unit basically combined with the unit in the middle becomes a 3-bedroom unit, and then the one in the middle becomes a master bedroom. So we basically create the series of compartments from the structure and they use that as the layout. Next slide. And then that was a penthouse. So these are the view of the interior spaces. Next slide. Next slide. That's the main view of this project, basically looking northwest towards the memorial and the World War Trade Center, and then looking at Hudson from the corner. Next slide. And then that's the kitchen. And then this is the studio unit. So which is this one in particular is looking south. with the punch window in the middle between. So this is concrete and that is concrete sheet, which is holding up the building. Next slide. Then we have amenity floor on top of the building, where we have screening room, dining, lounge, and the next slide. And also we have a pool looking down the Memorial and the World Trade Center, and then we have treatment room and the lounge area and the locker room, saunas. And above the pool, which is double height, we have workout area and a yoga studio and gym. So if you look at the rendering next slide, see that basically top of the building is the club. I think they call it Club 88 because the top floor is 88th floor, and then that's the view of the lounge. That's the screening room. And then that's the pool. And then the ground floor we have, by the zoning we had provided the cover arcade on the Thames Street site. So we basically widened the Thames Street site. It's more walkable now with the project itself. When the project is done, it's going to be more walkable. Right now it's like not even 3 feet actually, Thames Street is. Hopefully it'll get better with our project. And then this is a view of the lobby. And then that was the beginning of the project when the existing building was there in 2013. And then in August, we demolished the building. Next slide. And in 2014, construction started. All right, next slide. And then when the market changes, and then when we were changing between the rental to the condo, there was a little bit hold up. But the construction started back in 2016. And next slide, 2017. Now you're seeing the podium where we have lofts units. And the next slide. Last one is the photo I took a few weeks ago, which is pretty much right now. And then that's it for the presentation. Thank you for listening. And then I'm handing over.
Fingers crossed. I've got my timers. Most of my crew's here, so if I've got a problem, I'm assuming one of you guys in the front row is going to jump up and help. Thank you all for being here. My name is Stephen DeSimone. I'm with DeSimone Consulting Engineers. What I thought I would do, beyond getting into sort of the nitty-gritty and the things that we engineers find really interesting, I thought I'd stay away from that because usually nobody finds it interesting but us. And I thought I'd really start to talk, as Carol mentioned, about the concepts of what it takes to do these buildings, okay? I don't want to talk about numbers, but things that we've learned, and engineering is always evolving, and things that we've been incorporating through decades of doing high-rise buildings in New York to sort of master this particular typology of buildings. So I'm assuming we move forward. A little shameless promotion. These are some of the projects that we've done or doing here in New York. It's only 2 slides, I promise. But again, we've been fortunate enough in that we've been doing high-rise buildings. Again, my dad started from '69. So we've been at it quite a while. And more importantly, beyond being at it a while, we've got a great database of how these buildings perform. Okay? I always throw this in because you guys might have gotten snookered into thinking you were coming to hear about the design of a super tall. There was actually a CTBUH blue ribbon panel that determined that super tall actually has a definition, and that's 300 meters. And there's actually a mega tall category, which is 600 meters. But again, what does height really mean? And when we talk about height and the challenges of building tall, I like to think of it more in terms of slenderness, okay? The building to the left is the Shanghai Tower. That is a mega tall building. But when you look at the footprint, it's 242 feet at its widest portion, which gives it an aspect ratio of about 9:1. And again, Jin mentioned that our building, while it's 913 feet, it's 65 feet, maybe even less, puts the aspect ratio at about 14. So from a challenge standpoint, Not to take anything away from the Shanghai Tower, but the challenge, at least as we find it, is not so much in the height, or the absolute height, but it's more in the dimensions of the building, particularly the aspect ratio. I always start all my presentations, particularly when I'm speaking to students, and you all are students of high-rise. Buildings are just beams, and whether they're wide flanges or tubes, they're really, really actually simpler the taller and taller we go. And I say that facetiously. They're simpler in that we have fewer and fewer parts and pieces to rely on. There's less redundancy. And when I show you the plan for our building, we've got a shear wall and 4 columns, okay? It's relatively simple, but what that means is that you really have to get those 5 elements right, because there's little in the way of redundancy. So if you mess up 82 floors, you're making 82 mistakes, and they tend to compound themselves. Again, and this goes to sort of the theory, right? In our office, relatively quickly, when you look at a high-rise building, again, as a beam, a cantilever beam, if you will, you can really draw a circle around the ultimate solution using hand methods, right? Opening up a steel manual or a design manual, looking at the equations for calculating displacement and moment in a cantilever beam. You calculate your wind loads using the code, and you can really determine relatively quickly at least a ballpark of what the solutions should be. Okay? And that's an approach that we always take. I want to talk about the approach that we take for these buildings that's really different than we have been taking. The approach is different than what we used to take. And I call it a performance-based approach. Okay? And I call it that because, quite candidly, I'm not really that interested in how much the building moves. And I know that might sound counterintuitive. But when you look at design in years past, and when I came up, I've been at it 28 years now, we always sort of started with kind of a displacement-based approach, okay? How much material do we need to limit the overall displacement of a building? That was usually the height of the building divided by 500, which is a little less than 2%, okay? It was a great number, right? Because when you think of older buildings 30 years ago, or even further, when this sort of standard was adopted, and I have no idea where it came from. If anybody in the room does know where it came from, please let me know. But again, it made some sense, right? We were building buildings that were more brittle, right? We weren't using drywall for partitions. We were using terracotta brick with plaster. The facades were brick and block. They weren't curtain walls. So limiting the amount of motion or movement, if you will, that the building experienced made some sense. It also made some sense from the standpoint that our analysis ability, if you will, back then wasn't that great. So when you limit the overall displacement of a building, you also limit the amount of secondary effects that occur because of a lot of displacement. So recently we've sort of thrown all of this thinking out the window. Okay? Again, I don't really care how much a building moves. What I do care is how the building moves. Okay? And one of the performance targets that we use is accelerations, okay? Quickly, think of you're driving in a car, windows closed, music on, 60 miles an hour, you don't feel the speed. If you put your foot on the brake, you feel that deceleration. If you put your foot on the gas, you feel the acceleration. So if you think of a building moving in space like an inverted pendulum, right? It picks up speed, it decelerates, stops, and then starts all over again. Those are the things that occupants feel. They feel and perceive that acceleration and deceleration. So typically we like to limit that, okay? We use return intervals, particularly a 1-year wind and a 10-year wind, and we limit that performance or that response to accelerations measured in milligeules. That's 1,000th of the force of gravity. A lot of times we're always arguing, and you see 1 year is 8, 10 years 15 to 18. To me, when you're dealing in thousands of anything, the difference between 15 and 18 is round off, right? But I'll get a little into that. So again, these are the performance standards that we set for these high-rise buildings. Again, forsaking really all of the other things that we used to use. This is another interesting study that we've come out of a lot of the evaluations that we've done, is that long period buildings tend to respond differently than short period buildings. Okay? Short period buildings are squatter. The longer period buildings tend to be the high-rise buildings. I'm going to show you this little video, and you'll see, if anybody knows, that's Melissa Burton. So she was actually a student when these were made. She used to run BMT, I don't know where she is now. But this is a high-frequency, short-period building of a simple equal acceleration. Okay? So let's say that's 15 millig's for argument's sake. Okay? This is a longer period building at the same accelerations. Elvis doesn't seem to be responding that much. But so again, what we found is that we can push the boundary of that criteria with a longer period building more than we can with a shorter, stouter building. Okay? So what are the factors that affect building response? Shape. Okay? Buildings do not want to be aerodynamic. It sounds counterintuitive. You don't want your building shaped like an airplane wing, because if it's shaped like an airplane wing, it's going to generate horizontal lift or force that would rattle the building. Okay? Damping, and I'll get into what damping is. Damping is a way in which we flatten peak responses, similar to the activity or the action of a shock absorber in a car suspension system. Height, again, we're talking about that. Slenderness and weight. Okay? The weight of the building is important. Simply think of Newton's law, force equals mass times acceleration. Solve for acceleration, which is the criteria we're interested in. And the heavier the building, the lower the equivalent acceleration. Okay? Which is why most of the high-rise, the tall, super tall, mega tall buildings are made of concrete and not steel. Okay? This is a chart that we've developed through the years. And when you look, it's really about sensitivity. And when, I've got a pointer here, yeah. So when you look at the impact of adding mass, again, we want to change that denominator, right? If I add 30% mass to a given building, the accelerations change little, okay? If I add stiffness, which is akin to adding mass, the accelerations change very little. So little bang for your buck. And when you looked at the floor plates of 125 Greenwich, you realize when we're adding mass and stiffness, we're adding structure, which takes away from the saleable square footage. Okay, so we're very cognizant of that. When you look at damping, when I go from 1% to 3%, I get a radical change in the building response. Okay? So, when I look at shape, square buildings, I've got a video here. What we're concerned about is this phenomenon known as vortex shedding. Okay? When the vortices that organize on the corner separate at a period equal to the building, we wind up with a resonant condition which super excites the building. Okay? This is a video of what that is. Thank God, where are you, Josh? Thank God these videos are working. I appreciate that. Many of the presentations they don't. And again, these are generated from years of doing projects. And what does this chart tell you simply? Rectangular buildings aren't great. Circular buildings are the best, right? Nobody wants to live in a circular building because nobody can find a circular couch, right? So we're always looking at right angles no matter what. But generally, it makes a lot of sense. Think about a smokestack. Smokestacks aren't rectangular, they're round, okay? Because they perform better in the wind. For us as engineers, looking at sort of that round shape and taking it a step further, this would really be the ideal building for us. But that's why engineers are engineers and we're not architects, right? Wrong button. So these are some buildings that we've done, and Carol mentioned them, tall, super tall, call them what you will, but where we've integrated what we consider, we'll call shaping studies, right? We look at how we can make and modify the shape of the building to improve its performance, okay? So this is 50 West Street, and we had two moves here. We put a hole in the top, which you can see there, and then we simply rounded the corners, and this is what the building looked like originally. This is ultimately what it looked like in the built case, okay? This is a building that we did on 22nd Street with KPF. It was a shard-shaped building originally, and ultimately we wound up doing through a shaping study is we came up with a building with, I'm sorry, let me just jump back, with chamfer corners, okay, and that's the finished product. And you can see the chamfer actually changes with height. So what we're doing there is, the previous slide that I showed you with the vortices, what we're doing is we're confusing those vortices, we're preventing them from organizing on the corners of the buildings by constantly changing the shape of the building, okay? Now, what does that really mean, okay? This was the study that we did on 22nd Street. We looked at 19 different variations of building shape, okay? And originally when we went into the wind tunnel, we realized that we couldn't throw enough mass, we couldn't throw enough stiffness, nor could we throw enough damping at that building to meet the performance criteria that we set out at the beginning of the project. So you can't change the wind environment, you can't move the building from its site, so what we wound up doing is undertaking the shaping exercise. And ultimately what that did for us is it reduced the net effective force on the building significantly. So if we look at the bottom, the baseline model, which was sort of that extruded shard, had 1,900 kips of wind force at the base. Okay? By merely shaping it, we reduced that number down to 1,200. So a 30% reduction in effective wind force merely by changing the shape of the building. Okay? So those are the types of things that we've been doing on these high-rise buildings. So let's talk about damping. Okay, what is damping? This is probably just the best way to show what it is. So I'll be quiet. The left one's undamped. Enough of that. So this is actually a damper that we've got on one of our buildings. It's not a great video, but I'm going to play it anyway. Okay. And you can see the damper's hung from a pendulum. There's viscous material on the underside of the mass. And you can see how it... So Newton's other law says things in motion tend to stay in motion, things at rest tend to stay at rest. So essentially what happens is the mass of the damper wants to stay at rest, and the building wants to move underneath it. Okay?
What floor is that on?
That's at the roof, so it's probably about 800 feet in the air. Okay. Done with an iPhone, it's not like this. So, when we originally conceived this building, and Jaina talked about the difference between the BSA scheme and the as of right? The building was north of 1,300 feet tall. Okay? So normally what we do, or what we had done in the past, is we sort of try our best, we go to the wind tunnel, we get the results, we hope and pray that we don't need a damper, because dampers run anywhere from $2 to $4 million, and then we react. So at this height, we knew that we were going to need a damper, and we knew that we were going to have to shape the building. Okay, that was the only way that we were going to reach the performance targets that we had established and try to get it on the first try. So what we wound up doing, let me just go through this. So when we look at damping again, we assume 2% inherent damping in all our concrete buildings. Okay. What we found is that we get to, through artificial damping, we can add an additional 4%. And building response, this is where I'm getting into the engineering part, is inversely proportional to the square of the damping. right? So when you double the damping, you don't reduce the response in half. But when you go from 2% to 6%, you essentially can count on almost a 40% reduction in building response. Okay, so you get a lot of bang for your buck there. So what we typically do is, again, we almost work backwards. We reverse engineer it. We say, all right, we know that we can get 6% damping. We know that our target response is 18 milligis. What does the building need to do? How does it need to respond undamped? Okay, we do the math backwards and we say, hey, listen, if we can get to 32 milligis undamped, we know that we're in striking distance. Okay, so this was the building in the wind tunnel. I don't know if anybody's ever seen a wind tunnel. It looks nothing like you see in the Ford commercials with the smoke and the white lab coats. It's like akin to watching grass grow because you can't see wind. Very disappointing. So again, what we do is we build a 1 in 400 model. We build 400 yards around the building. A lot easier now that we have Google Earth. And then the model itself is actually on a turntable. So we turn the building through the wind in 10-degree increments. It's on a little pivot at the base, and it moves in the wind. We do an eigenvalue calculation. We calculate all the responses. Again, all the stuff engineers like to talk about. But these were some of the different concepts that we came. At one point, we were even talking about an antenna, a spire, a wind turbine, right? So we tested all of these in the wind tunnel. And again, one of the things we did is we said, listen, what is the value of shaping? Okay, so what we did is we looked at an extruded shape. We looked at a shape with the windbreaks. Okay, and then we looked at a shape with rounded corners. Okay, what is the sensitivity to this building in its environment, incorporating those various shaping options? Okay. What we found out really quickly, and I hope I didn't miss a slide, is we wound up ultimately, I shouldn't say ultimately, we wound up on the first shot getting the building to meet the performance criteria utilizing all these shaping techniques, which for a building of this height is really unheard of. So we wound up taking some of the precedent that you guys had at 432 Park, some of the precedent that we had on other projects that we had worked on. We incorporated that into the shape and we got it on the first go, which was, again, sort of unheard of. And you can see, just quickly, we're at 19 milligis at 1,400 feet of height, which is pretty good. Okay. And again, what did those different moves do for us? So I told you we had sharp corners. That was sort of our baseline in black. Rounded corners, we got about an 8% reduction in wind force. Okay, when we combined the rounded corners with the blow-through floors, we got up to a 20% reduction in effective wind force on the building. So these moves really matter. I think they make the building look cool, but we're doing it for a reason. So the next time you look at a building and you see round corners, you see a pop through the top, you see these blow-through floors, it's less about architectural expression and more about aerodynamics. And again, back to that slide I showed you where I say buildings are wide flanges or boxes. This building is all about a wide flange. And Raphael had very, very strong opinions about what the structure of this building would be, which is actually a good thing. Because when we're working with and collaborating with architects and owners who know about what we do, understand the challenges that we're confronted with, it makes for a better solution, but a faster convergence to the solution as well. So ultimately, this was one of the solutions. This was the super tall version, the 1,399 foot. And essentially, it was sort of these wide flange beams, okay, elevators in the core. And what we ultimately did is we eliminated all the columns to get the load into the core. When the core is loaded in compression, we don't get tension, which means we don't get cracking, which means we ultimately wind up with a stiffer building. So this is where I tell you these buildings are relatively simple, okay, because it's 2 wide flanges. But the fact that they're only 2 wide flanges means we really, really have to get it right. And the wind tunnel testing is a part of that, okay? So, unfortunately, we didn't get to build the 1,399 footer. The super tall, the true super tall. So we wound up, I don't know ultimately where we're at, 912, 940, or, well, and there's rumor that we don't really know where we're going to be at the end of the day, but that's a different story. So this was all, so what was interesting is we understood the value of those moves. We understand the value of the shaping, the rounding the corners, the blow-through floors, right? And they became integral not only to our solution, but to the architecture as well. So when we shrank the building, we knew we were still going to get that value, and it was still going to provide us with benefit. We did need, ultimately, to still include a damper, but instead of, I'm hoping I got this image, instead of the big $4 million pendulum damper, we're using a unidirectional slide friction damper. This is actually the one similar. This is actually the one we have in 50 West Street, but this is a $600,000 damper as opposed to like a $4 million damper. So again, we knew we needed to have damping to reach those performance targets, but because we integrated all of those beneficial moves from the higher building into the shorter building, we needed a lot less damping. This is ultimately what it turned out to be. We scrapped the idea of not having columns, but we only have 4 columns, which again means we've got to get those 4 right. Probably smaller than I would like the columns, probably larger than you would like them, but that's the battle, right? Right? That's the battle that we fight with the architects. But again, simple, clean. What's interesting about the building as well is you would think that the views are north-south, but east-west is really the best. And that sort of informed the direction of the structure. And again, pretty clean. Ultimately, for us, you know, when we think about the design and we roll over into constructing these buildings, we're 88 typical floors, right? So again, you make a mistake on one floor, you repeat it 88 times. But in terms of making these buildings cost effective, it's about simplicity. Okay? How do we get from the 2nd floor to the 88th floor as fast as possible? Okay? New York is a high labor market, not relative to material. We could spend a little more on material to save on labor. Okay? So again, hence the reason why this is relatively simple plate, simple structure. This is what it looks like as we go up. Things get smaller, apartments get bigger, so it makes sense. You've seen these images. What's interesting is let me just jump back quickly. The walls that make up, the flanges that make up the wide flange, the architect didn't talk about this. It's actually architecturally exposed concrete, okay, which posed some really unique challenges for us. These are architecturally exposed concrete. You can see the mock-ups that we had built, full-scale mock-ups. What was interesting for us is we're trying to not only assure that we're getting a particular concrete strength, we're also looking for concrete modulus, which is the stiffness of the concrete, and we're trying to match a color and the finish. So, what did I say? Color, finish, strength, modulus. We actually only got 3 of the 4. So, we got the color, we got the strength, we're battling the modulus, but we've got some safety in our pockets. But again, these are the challenges that when we go from, I still say pencil to paper, to the field, that is the next sort of challenge for us. And again, normally on these high-rise buildings, we're not focused on, we're focused on strength, we're focused on concrete stiffness or modulus. We're not concerned about what the concrete looks like. So adding this extra bit of complication was a real challenge from a concrete supply standpoint. This is the hole. Again, super tight site. These were the shear walls up against the American Stock Exchange. Millions and millions of dollars just to hold the hole open. keep the streets alive. All that steel unfortunately just gets thrown out. Here they are. Again, you can see, look at the equipment. 3 pieces of equipment on a super tight site, which was a real challenge. These are the caissons that went to rock, 36-inch?
Yes,
Please, okay. How far down?
60,
Okay, so
60?
60 feet down the rock.
40 feet high.
Yep, with a 40-foot socket. Okay, so, you take 88 floors, or 88 levels of concrete, and you're concentrating on a tiny little footprint. The stress per unit area is really high. Okay. Again, you can see here we're using prefabricated high-strength reinforcing gauges. 28 minutes more. Again, you can see the caissons, the high-strength rebar with the couplers, which is a relatively new mechanism, a new material that we use in the city. The great thing about the couplers is it eliminates the splices, eliminates congestion, reduces the total amount of reinforcing steel in the building, so we like that. These are the walls starting to come up, some of the concrete. Here you get a good sort of sense for the floor plate. I don't know where we took this, but that's a great shot. You can see the one flange coming up. Here we've got a little bit of a cantilever. I forget why we did that, but we did it. This is how we're supporting the crane. Again, this is Thames, which is super narrow street. It's more of an alley. I don't know why they call it a street. So we have to actually hang the tower crane off a bracket from the main core wall. Okay. When I'm getting my Starbucks, I walk around the block.
They were jumping the crane last night,
Well, there
right
you go.
past there. Yeah.
Just some more images, right? And you're watching it all sort of come together. These are the link beam steel between the 2 flanges. Here you can see, now we're not in mock-up mode anymore. We're in the actual mode of stripping, and I think the architectural concrete looks pretty good. You're not shaking your head. Like I said, we got 3 out of 4 things right. But now you start to see the real views, right? And again, column-free corners. We used a thicker slab here to minimize the total number of columns, to maximize the views, because ultimately the building's about the views, right? And again, it's really, our client's not here, but part of our job also is trying to understand not just what we do as structural engineers, but what's the plan for the building? How are we going to market this building? What is the demographic? What is it that's really important? And here, because of how we place the core, those corners really became super important in terms of the layouts and in terms of sort of preserving those views. You can start to see it coming up now. I don't know how far along. Are we at the halfway? No.
36,
Okay. 30
second floor.
out of 88. Okay, so we got a ways to go yet. I guess that's it. All right.
Yeah. I bet there's some questions. Are there questions?
Floor to floor.
What
In the
is the floor to floor?
Typical floor to floor.
11.5? 11.5 inches. Yes. 11 feet 5 inches.
So there really are 88 levels. You didn't cheat by starting at 15 or something.
For the marketing floor?
Yeah.
We're skipping floors for the marketing, but not because of the floor to floor height. Floor to floor is actually tall, but our podium is actually we have very tall spaces in the podium. We have 20 feet, 30 feet spaces in the podium, so we're skipping a few floors for the marketing floors.
So I guess the question is the 88 determined from the marketing or the construction?
88 is determined by the marketing, yes.
And in this day and age, we're still avoiding the 13th floor. If you can believe that, right?
was the 88 chosen for Lucky Eights?
I didn't choose, so
Could
probably
be.
our client.
That sounds good, Carol. That's
Okay.
it. We need a backstory for 88.
Okay.
You must have studied the reflective light off of the World Trade Center buildings, because if you're facing north toward the World Trade Center and the sun is in the southern sky,
Mm-hmm.
you get that tremendous reflective light hitting your building.
So for the residential building, it's not like an office building where occupants are staying in the building during the daytime. When you design the residential building, the aspect you're looking at for the enclosure is the basically performance of the performance for the glare. So what we use in this building for the residential is that we also use very reflective glass. So during the daytime you get you get less heat and then less glare from inside for the occupant, but you have maximum clarity at night. So we also use the reflective glass for the closet.
You can mention the showroom to them in case anybody wants to go
Oh, yes.
see
So,
it.
yeah.
Purchase a unit, yeah.
right?
Yeah, since our client is not here, be in the marketing mode that we have sales office of our project in 84th floor of the World Trade Center, One World Trade Center. So you can visit our website, visit their website for the sales, and then I think you can make a reservation for the tour, or you can tell them you're a potential buyer and then want to take a look at the unit. So we have a full-size mock-up unit of the 3 units. We have a 1-bedroom unit, we have a studio unit, fully mocked up. All the windows are built, kitchens and everything is built, and it is fully also furnished with our interior designers, furnitures and things, which is quite a thing to look at. And then we also have a view of the site from our sales office because it is in the World Trade Center. So if you have time to visit, it is a good place to visit.
So, Stephen, that was incredibly clear, but much of it's still over my head in terms of the engineering.
Me too.
Okay. But one question I have is, if you were doing pure engineering rather than engineering for the economy of this particular site, is there anything different about the concrete, or I guess especially the concrete and the way the stiffness of the structure that you would have changed?
Well, so I think the lateral system of the building is pretty pure in that if you think about all the research that went into determining the shape of a wide flange, we just sort of co-opted that, right? I think when you think, we talk about efficiencies and optimization, right? It has different meanings in different locations, right? So you can optimize the use of materials, or you can optimize the use of labor, or you can look at the aggregate and just optimize cost. So in other markets, instead of doing a thick flat slab, we made in Asia or in Turkey or in Latin America, we might have used a beam and slab system. It would use less material, but it would be significantly more labor intensive, if you will. But again, those systems don't really lend themselves well to residential because for us, you're trying to stack as much. We had a height restriction ostensibly, so you're trying to stack as much floors into a certain volume. So the thinner the sandwich, the better. And in a concrete building, the underside of the slab, we just put Cadex right on it, and that becomes the finished ceiling. So I'm not a big tube guy. Like, I went after 432 Park, and my solution was totally different than that one, okay? I lost. So I like what we came up with, ultimately, because I think, again, it's this discussion of optimization of materials versus aggregate cost versus, look, we're working on high-rise buildings where a developer says, I'm going to give you $25 million extra to spend, create something spectacular, right? So, because he's selling it $8,000 a square foot. So, I like what we had on this one. This one feels right to me. So I wouldn't have done anything different. Maybe charge them.
Can you reveal the per square foot construction cost? Do you know what it is? Or ballpark?
We don't have finalized number yet, so I can't really discuss the number. Yeah.
Ballpark? Is
No,
it a
no
lot more
surprises
than
on the structure, I'll just
Yeah.
tell you that.
It's
I don't
not-
know.
There's nothing, extraordinary about this cost of the building. Just
But there's got to be a premium for slenderness compared to a 40-story tower. right?
Oh, if you compare that, yeah. But if you compare it to the other slender tower, this is nothing special.
Okay. Are there any other questions? If not, you can ask questions individually. We'll have a reception over there in that corner. And let's all thank our speakers again because it's great. We settle in, let me begin to welcome you. I'm Carol Willis. I'm the founder, director, and curator of the Skyscraper Museum. How many people are here for the first time tonight? Well, a few. Okay, well, welcome. If you would come in the correct way of the Promenade Architecturale, you would have come up the ramp and into the space around here and seen that we have an exhibition right now that I hope you'll take a look at after the talk. And we'll also have a reception called Millennium Lower Manhattan in the 1990s. And for those of you who don't know the museum, we like to alternate between New York City history and more international and contemporary subjects. We also do public programs once a month, which are book talks, and our next talk is on New York waterfront, which will be in late May, actually. But this evening, as a lot of you know, because you're part of our corporate members, either in architects, engineers, developers, builders, we run a series that we call Skyscraper Seminars. And in those programs, we like to really explore in depth the single building or a particular building type with the depth of information and understanding that a real seminar, a real professional seminar would undertake. And so this evening is another one of those series, as you know, about 125 Greenwich Street, in the same series in which we also began to explore way back in 2013 a new building typology, which I'm a historian, I assert is an entirely new typology in skyscraper history, and that's the super slender, and that's usually paired with ultra luxury residential tower. And 125 Greenwich is one of that type. These buildings are characterized by their slenderness rather than by their height. And the slenderness in terms of engineering, because Stephen DeSimone will be talking in detail about the engineering, are very particular, have very particular requirements. And in their architectural design also require certain strategies of floor plans and fenestration and materials that have developed in New York, and I would argue only in New York, let's say I have argued many times only in New York, as a very distinctive form, new form of the skyscraper. There are slender towers around the world, certainly in Hong Kong. There are very tall towers that are also slender. One thinks of Dubai and those residential towers that are 1,000 feet, 300 meters or taller. But it's only in New York that this super slender typology has developed. And if you want to look on our website back at the exhibition that we did in 2013, when only one of these towers, 157, had been completed, there's an exhibition called Sky High and the Logic of Luxury. And tonight fits in that series of documenting the evolution of this type. And we're very lucky to have from Raphael Vignoli's associates, Jian Choi, who will talk about the design from his perspective as the project manager on the project, and will show us the genesis of the design and also the evolution as it crossed over from from about 5 or so years ago to its present state today. So the focus of this evening is really to get into the nitty-gritty of some of the design issues that that challenge this building type, and to get on the record, so we're filming tonight, to the documentation by the designers themselves of this process. So, so following in that series, when Raphael Vignoli spoke about their earlier design for 432 Park Avenue, or Greg Pasquarelli from Shop talked about 111 West 57th Street, this is our way at the Skyscraper Museum, I hope, doing some serious academic research and documentation and archiving of this particular phenomenon. And so I'm going to get out of the way quickly after I do very brief introductions of Jayan and Stephen, so because I've seen their slides and they have just an enormous richness of detail of the various aspects of the research involved in these projects. So first speaking will be Jayan Choi, who is, are you a principal, what's your, I'm sorry, your title? The project manager.
Let's make him a principal.
This we'll make him But he's been with Vignoli Associates for 8 years now and has worked on many of these residential projects. He is architect, educated at Cornell, and has had an enormous amount of experience in these important residential projects, and really in every aspect of executing the design. Second to talk will be Stephen DeSimone, who is the president and CEO of DeSimone Construction, DeSimone Engineers, and he has been with the company, which you get the idea is called DeSimone, since 1988, but the firm goes back to 1968 because it was started by his father, Vincent DeSimone. Stephen happens to serve on the board of the Skyscraper Museum, so I'm able to impose on his goodwill. He has worked on all sorts of projects, but the residential towers in New York, of which I had to write down even a few, of this slender type include 50 West Street, which is right up the block, a couple of blocks away, 111 Murray Street, a KPF project which is just a little bit farther up West Street, 220 Central Park South, the Broome Street building, the Zaha Hadid high-rise on the High Line, and 100 East 53rd Street, a Norman Foster design that is right behind the Seagram building, but it's white instead of black. But you didn't have anything to do with the color, probably. But all of these examples, except the Zaha, all he did a Zaha project in Miami, where he also is doing, their firm is doing an enormous amount of high-rise work, all develop this particular form with some of the world's greatest architects and kind of leading designer names. So DeSimone has specialized in these design challenges, as with Raphael Vignoli Architects, in any number of projects, and I certainly urge you to go to both of the firms' websites in order to see really some of that extraordinary work. So with that, I'm going to let Jayan start the talk. There, sorry.
Hello, everybody.